So in the pre-lab for the coffee filter, we talked about an object that was falling, and we said once that object has hit its terminal velocity, then we would have the force of gravity going down that would have to be equal and opposite to the drag force going up. What we want to talk about in this set of video notes is we want to find the equation for the velocity before it has hit that terminal velocity. So if we're drawing a force diagram, you could picture that this drag force is less than the force of gravity. So when we start out, we're going to start out with Newton's second law equation, that F equals ma. We'll have that the gravity minus the drag is going to equal mass times acceleration, but the gravity is going positive because that's the way the diver is moving or the object is falling. Then we can say, hey, didn't we talk about earlier that this force of gravity is mass times gravity? And then the drag, we can say that is that constant times the velocity. Now we're going to simplify the coefficient, or not the coefficient, the exponent that we talked about earlier. We're going to say that it's 1 just to make life easier in this case. We also then want to take and say, isn't acceleration really the differential or the derivative of the velocity with respect to time? So if I'm trying to find the velocity, I have to split the acceleration back into that differential equation. So I'm going to say m dv dt for that right side of the equation. The problem with that is I notice that there is a velocity on both sides of those. So I want to get those two velocities together. I'm going to split my differential and move my dt to the other side, move my m to the other side, and then divide both sides by that mg minus bv to put it onto the denominator of the velocity. So now I have on this side, on the left side, I have the things that I can integrate with respect to the time, and on the right side, I have the things that I can integrate with respect to velocity, specifically that dv and the v that's there. So I'm going to integrate both sides of those. The left side of that becomes really easy. I can pull the 1 over m out and then integrate dt, which is just t. I'm going to add a constant because it is a indefinite integral. I had to think there for a moment. Then on the right side, it's not quite so easy because I can't just integrate this denominator because it has that value. Now, there is an integral that we do know, and that is that the integral of 1 over x dx is equal to the natural log of x. So if we can get this to look like that, then we could potentially easily integrate that. So the way I'm going to do that is I'm going to use a type of calculus called u/du substitution. I'm going to set my denominator equal to the u value. That way I can put in u in the denominator, and I'm one step closer to this 1 over x value. It would be 1 over u in this case. But then I need to get my dv in the numerator with respect to the u value. So I'm going to take the derivative of u with respect to v. Remember that this is a constant. It goes away. And the derivative of the second term will just be the negative b. This should be a negative lowercase b. So if I solve for dv, I get du over negative b, and I can plug in both of these values then back into the equation. So the denominator becomes u, the numerator becomes du over negative b, and then I can multiply both sides by the negative b to put it out because it's a constant. And then it technically multiplies into that constant also, but it's a constant, so I can just leave it written as a constant. Now I have this integral of 1 of the du over u, which essentially is this that we said earlier. So we can say that the negative btm is the integral, or is the natural log of the u value. Don't forget, it is also an indefinite integral, so I'm going to have to add a constant to it. Now, looking ahead, I'm going to specifically make that constant look very specific. In this case, I'm going to say it's minus the natural log of c, because eventually I'm going to have to get rid of this natural log. And if I do minus the natural log of c, I can do some logarithmic identities in order to not lock my c value into the e when I want to get rid of the natural log. So remember, the log identity is the natural log of one variable minus the natural log of another variable is the natural log of the first one over the second one. So I can simplify this left term into this. Now to get rid of the natural log, I'm going to do e to the both sides. So if I do e on this side, that will go away, and I'm left with 1 over c. And now you can kind of see why, to begin with, we did this minus c value for that. So then I'm going to multiply both sides by c. When I do that, I can resubstitute my u value back in. So I'm going to say mg minus bv on the right side. And the next step then is to find out, well, what exactly is that constant? How can I figure that out? So at time equals 0, then remember e to the 0 all simplifies down to become 1. And at time 0, what is our velocity? Well, our velocity is 0 at time 0. So can't we say that the c value is just that mass times gravity? When we do that, we can resubstitute that back in, so mass times gravity over here. And remember that the whole goal of what we're trying to do is we're trying to find this velocity before it hits terminal velocity. So I want to solve for v now. So I'm going to swap this to this side, swap this over here to this side, and I'm going to have bv equals mg minus mg e to the negative bt over m. Pull out the mg's and divide both sides by b, and I end up with an equation for velocity here that is a logarithmic function. Now, the other thing that I might notice on that is to say, hey, what happens as the time approaches infinity, which is really I'm looking at, well, when am I going to hit terminal velocity? So as the time approaches infinity, then remember that e to the log of infinity is going to become 0. This whole term just becomes 1. And I'm left with a terminal velocity that is equal to the coefficient that's in the front, which would be mg over b. So oftentimes you'll see this equation written not like it is here, but you will see it written down here where they'll substitute that mgb value. Now, interestingly enough, remember back in the last one, whenever we had the drag was equal to the gravity, so we said that gravity was equal to the force of the drag. The mass times gravity equals bv, which is at the terminal velocity, then doesn't that equation simplify into that equation? Or even still, doesn't this equation simplify into that equation when we hit terminal velocity? Very interesting to help prove and show that we did it correctly and we're on the right track. Now, the last thing that we would want to talk about is, okay, there's our velocity equation. Couldn't we take and find our position equation from that, or find our acceleration equation from that? And that just goes back to what we studied in the kinematics chapter. So if I have a velocity function, how would I find the position equation? Don't forget that we would integrate this velocity function in order to get that. And if I want to find the acceleration from a velocity equation, then I would derive that in order to get the acceleration. And I'm going to leave that up to you to see if you can figure out how to do that. So in essence, we are finding two different scenarios. In the coffee filter lab, we're setting the drag equal to the gravity, finding the terminal velocity. And in this scenario, we're saying, well, up before we hit terminal velocity, how would we determine what the velocity is at any given moment before it hits terminal velocity? Now, even still, this equation is the more general of the equations, because doesn't it include even after you've hit terminal velocity, then it simplifies down to be just the terminal velocity equation.